World War II is often remembered for standardized mass production, yet a significant portion of wartime weapon development moved in the opposite direction, across all major powers. Dozens of systems were created that could not be produced at scale due to material shortages, industrial limits, or unresolved technical complexity. Archival production data shows that some advanced designs never exceeded double-digit manufacturing totals despite proven battlefield relevance. This catalog presents a complete and structured overview of those weapon systems conceived for decisive advantage, engineered under wartime pressure, and constrained by the realities of industrial war. This catalog is confined strictly to the period of the Second World War, from 1939 to 1945, with limited references to immediate late war testing in 1945 where relevant. The geographic scope includes the primary theaters in which these systems were developed or intended for use: Europe, the Pacific, and North Africa. Organization follows functional and technological roles rather than nationality. Grouping weapons by operational purpose and developmental logic included are aircraft, missiles, naval weapons, ground systems, and electronic devices that failed to reach mass production. Excluded are post-war deployments, purely conceptual proposals, and weapons that achieved full industrial-scale manufacture. The first group addresses aerial interception and strike systems whose designs exceeded the industrial tolerance of wartime manufacturing. These weapons were created to counter specific operational problems that conventional aircraft and munitions could not solve efficiently. Messerschmitt Me 163 Komet Germany 1940 for per-point defense interceptor. The Me 163 was developed to counter high-altitude, Allied bomber formations that conventional piston fighters could not reach in Me. It was designed to achieve extreme climb rates through rocket propulsion rather than sustained flight. A distinctive feature was its volatile bipropellant fuel system, which caused as many losses on the ground as in combat. Its operational impact was limited, yet it demonstrated the feasibility and cost of rocket-powered interception compared to traditional fighters. Messerschmitt Me 262A1 A Germany 1940 for per-jet fighter interceptor. The Me 260 was developed to overcome the speed limitations of propeller-driven aircraft and intercept bombers with minimal exposure time. It was designed to exploit jet propulsion before the supporting industrial ecosystem was mature. Chronic engine life measured in hours, not weeks, made large-scale deployment impractical. Despite limited numbers, it established the baseline configuration for post-war jet combat aircraft. The next group focuses on precision-guided, anti-ship, and anti-infrastructure weapons, representing early attempts to replace mass bombardment with targeted destruction. Ruhrstahl SD-1000 for 100 Frisch Germany 1943 per radio-guided anti-ship glide bomb. The Fritz X was developed to defeat heavily armored warships that conventional bombs could not penetrate. It was designed to be manually guided by the bombardier after release, correcting its trajectory via radio signals. Its most notable success was the sinking of the Italian battleship Roma in 1943. While tactically effective, it required air superiority and skilled operators, limiting production scalability. Henschel's 293 Germany 1943 per power anti-ship glide weapon. DAS 293 was developed to attack lightly armored vessels from outside heavy anti-aircraft zones. It was designed to use a rocket boost phase followed by guided glide, extending standoff range. The weapon's reliance on uninterrupted radio control made it vulnerable to emerging Allied electronic countermeasures. Its conceptual legacy directly influenced post-war anti-ship missile development. As air defenses improved, nations explore unconventional delivery systems intended to bypass interception entirely. Yokosuka M-XY7 no Kayapan, 1945. Piloted rocket attack aircraft. The Oka was developed to overcome Allied naval air defenses through terminal speed rather than survivability. It was designed to be carried close to the target by a bomber and released for a high velocity dive. Its extreme speed complicated interception. but its dependence on vulnerable carrier aircraft sharply limited operational success. The system reflected a strategic trade-off between manufacturability and expendable effectiveness. The following chapter addresses armored fighting vehicles that exceeded logistical and industrial feasibility despite battlefield ambition. Panzerkampfwagen 8 Messerschmitt Me 1940 per super heavy tank. The MAS was developed to create an armored breakthrough vehicle immune to contemporary anti-tank weapons. It was designed around maximum protection rather than mobility or transportability. Weighing nearly 190 tons, it required specialized infrastructure that did not exist in combat zones. Only 2 prototypes were completed, but the project illustrated the upper physical limits of armored vehicle design. T-28 Super Heavy Tank United States, over 1945. Assault tank prototype. The T-28 was developed to penetrate fortified German defensive lines without reliance on maneuver warfare. It was designed with extremely thick frontal armor and limited speed. Although mechanically functional, it arrived after the strategic requirement had vanished. Its development informed later American thinking on assault vehicles and engineering trade-offs. Attention then shifted to naval warfare systems whose complexity outpaced wartime shipbuilding capacity. German Type 21 U-boat Germany 1940 per electro-submarine. The Type 21 was developed to restore undersea dominance lost to Allied anti-submarine tactics. It was designed to operate submerged for extended periods rather than surface frequently. Innovative battery capacity and hull design made it technologically advanced, but production required precision manufacturing. Germany could no longer sustain its influence on post-war submarine design was substantial. I4O class submarine Japan 1940 per submarine aircraft carrier. The I4O class was developed to conduct long-range surprise strikes against strategic targets. It was designed to carry and launch aircraft from a submerged platform. The system combined multiple complex technologies into a single hull, stretching production timelines beyond wartime feasibility. Its operational impact was negligible, yet it remains one of the most ambitious naval designs of the era. Electronic and sensor-based systems formed another category that proved difficult to industrialize under combat conditions. German Wurzburg-Reese Radar Germany 1940 per fire control radar. The Wurzburg-Reese was developed to improve anti-aircraft accuracy against high-altitude bombers. It was designed for precision tracking rather than wide-area surveillance. Its large size, delicate components, and vulnerability to electronic jamming restricted deployment. Nonetheless, it represented a transitional step toward integrated air defense networks. Allied H-2S Radar United Kingdom 1943 per ground mapping radar. H-2S was developed to allow bomber navigation and target identification through cloud cover. It was designed to convert radar returns into real-time terrain images. Early models were unreliable and required constant technical support. Despite these limits, it reshaped strategic bombing doctrine and accelerated electronic warfare development. As conventional weaponry reached diminishing returns, experimental systems explored remote control and autonomous tech concepts. German Goliath SD.KFZ.302 Germany 1942 per remote-controlled demolition vehicle. The Goliath was developed to destroy fortifications and armored vehicles without exposing infantry. It was designed to be wire-guided over short distances, carrying a high explosive charge. Its slow speed and vulnerability limited battlefield effectiveness. The concept, however, anticipated modern unmanned ground systems that guided bomb SWAT Mk. 9 United States 1945 per radar-guided anti-ship bomb that was developed to enable autonomous target acquisition against naval vessels. It was designed to use onboard radar homing rather than manual guidance. Limited testing occurred before the war ended, preventing large-scale production. It marked a decisive shift towards self-guided precision weapons. Each of these systems emerged from a specific operational gap and pushed beyond what wartime industry could reliably reproduce. Together, they illustrate a transition from quantity-driven warfare toward technological asymmetry, setting the conditions for the next phase of weapons development. These late-war systems reveal a consistent pattern: innovation accelerating faster than industrial stabilization. Their value lies less in wartime results and more in the technical pathways they opened for post-war military engineering. By the middle of the war, a clear inflection emerged across all major powers. Traditional doctrines based on mass, redundancy, and incremental improvement were no longer sufficient to offset enemy adaptation. Radar-guided defenses, dispersed naval formations, and hardened ground targets reduced the effectiveness of standardized weapons. In response, designers shifted toward systems intended to compress decision time, extend engagement range, or bypass defenses entirely. This transition reframed weapon development from industrial replication toward technological leverage, redefining what effectiveness meant under late-war conditions and shaping the systems that followed. The final phase of development during the war concentrated on systems conceived too late, too complex, or too resource-intensive to reach maturity. These weapons were often technically viable, but misaligned with collapsing industrial capacity or rapidly changing strategic conditions. Aggregate for V2 Rocket Me 1940 for per ballistic missile. The V2 was developed to strike strategic targets beyond the reach of conventional aircraft. It was designed to follow a ballistic trajectory, making interception impossible with contemporary defenses. Production consumed disproportionate resources and relied on precision manufacturing. Under wartime disruption, while operationally limited, it established the foundational architecture of modern ballistic missile technology. Wasserfall Fernschlicht Flak Rocket Me 1945 per surface-to-air guided missile. Wasserfall was developed to counter high-altitude bomber streams more efficiently and conventional anti-aircraft artillery. It was designed to use radar guidance and command control from the ground. Technical immaturity and fuel instability prevented operational deployment. The program directly informed post-war surface-to-air missile research. Rheinbote Rocket Me 1940 for per long-range artillery rocket. Rheinbote was developed to extend artillery range without increasing gun size. It was designed as a multi-stage solid-fuel rocket, an unusual configuration for its time. Accuracy was poor, limiting military value. Its importance lay in experimental staging concepts, later refined in missile systems. German Missile Composite Aircraft Me 1940 for per composite strike system. The missile system was developed to deliver large explosive charges against hardened targets. It was designed by pairing a piloted fighter with an unmanned explosive-laden bomber. Operational complexity and limited accuracy restricted effectiveness. The concept anticipated later standoff and drone-assisted strike methods. Lippisch P.13 a Germany 1940 for per ramjet interceptor concept. The P-13A was developed to achieve sustained high-speed interception beyond turbojet limits. It was designed around ramjet propulsion and unconventional fuel concepts. The project never progressed beyond wind tunnel testing. Its aerodynamic research contributed to post-war supersonic studies. These late-war systems reveal a consistent pattern: innovation accelerating faster than industrial stabilization. Their value lies less in wartime results and more in the technical pathways they opened for post-war military engineering. Across all theaters and combat domains, the weapons that could not be mass-produced during World War II reveal a consistent design trajectory. They emphasize specialization over versatility, precision over volume, and technological leverage over industrial repetition. These systems were not anomalies, indicators of an approaching shift in how military power would be generated and applied. Constraints of time, resources, and production prevented their widespread use, yet their concepts endured together. This catalog reflects the transition from industrial-age warfare toward a model defined by guided systems, electronic control, and asymmetrical advantage. A complete understanding of modern weapon design begins with these constrained experiments.